think we'll make a start then. So my name is Eve and I'm the Education Officer at the OR Society, and I am mostly just here today to provide a bit of tech support and be a disembodied voice asking questions. The main presenter today is Matthew Robinson. Matthew works for IBM and he has been a member of the OR Society for quite a long time now, and he has very kindly volunteered his time today to run our Swede build presentation. So over to you, Matthew.
Thank you very much, Eve, and good afternoon. Hello, everybody. Yes, I'm Matthew Robinson. I'm here to take you through the Lego Furniture Factory. So hopefully, if you want to join in with doing this today as part of Maths Weeks England, you will need your Lego bricks. So what is the scenario we're going to be looking at? It's a company called Swede Build, and we'd like to launch a new range of dining furniture that's going to include some tables and some chairs. If it helps, think of this as somebody like IKEA. So when you think about a company like this, they are looking to launch this new range of furniture. So they want some tables and they want some chairs. So they have to think about what they're going to build the tables and chairs out of, which might be called the raw materials, and then also understand the costs of actually building these tables and chairs. So what we're going to be doing today is actually how we can model that. And what do I mean by model it? If you think of a company like Swede Build or IKEA, they cannot just go ahead and manufacture things. They need to understand what raw materials they're going to need, how much it's going to cost, what profit they may be making from building and developing all of these pieces of furniture. So they may model it first, and by that I mean build some computer models to help them understand. So what we're going to do is we're going to do a little model today to help Swede Build understand what's going to be the best way for them to manufacture these tables and chairs. So we should have some Lego, and these are in turn going to be the resources that the company is going to use. So, all being well, if you're working alongside this, you should have 6 rectangular Lego bricks. So these are blue in my case. So I've got 6 of those, and I've got 8 of the square ones, red ones in this case. So to start building our model, these are the resources that we have available to us. And Swede Build have decided that in order to build their tables and their chairs, to build a table, we're going to have 2 rectangular bricks and 2 square bricks. So in other words, a table will look a little bit, I don't know how well you can see this on the camera, will look a little bit like that. So it's got 2 of the blue rectangular ones and 2 of the red square Lego bricks as well. So that's a table. To build a chair, slightly differently, they're going to have 2 square Lego bricks. So that's 2 of the red ones and 1 rectangular one. So again, they will look like that. So reminder, that is the table and that is the chair. Now, bearing in mind that I started off with 6 rectangular Lego bricks and 8 square ones. So I built 1 table and I built 1 chair, which therefore means I've got 3 rectangular pieces left and I've got 4 square. Now I could, if I wanted to, use these spare ones to make another table. So if I just take those very quickly and I build another table like so, I've now got 2 tables and a chair. And I've also got 1 rectangular and 2 square bricks left. So I'd like to take a couple of minutes now to think about you've got all of these rectangular pieces and you've got all of these square pieces. How many tables and chairs do you think you can make? So you may decide that you're going to use the bricks that we've got, the rectangular pieces and the square pieces, and you're just going to make tables. Or you could say, I'm going to use all of them and just make chairs, or a combination of the two. So what I'd like you to do now is just spend a couple of minutes, and obviously this exercise can be repeated afterwards if required. So I want you to take your Lego and I'd like you to try and work out the number of different combinations that you can make with those bricks. Now, some of the combinations, you may end up with some pieces left over. So again, just note down how many pieces, for example, you got left over. So say you may start off by saying, I'm just going to build all chairs. So how many chairs can you build, and do you have any pieces left over? You may decide, I want to build all tables. And again, you may have some pieces left over. Or you might say, I'm going to build one table and I'm going to use the rest of the bricks to build chairs, etc. So you can understand what we're trying to do here. These are the raw materials we have available to us. And what I'd like to do, or like you to do, is to think how many tables and how many chairs you could actually make from these. So get building. And I say, I'll just give you a minute or so just to do those, and then you can work through how many tables, how many chairs you can possibly make with those resources you have available to you. So this is going to be the first part of our modeling example by looking at the possible combinations of tables and chairs you can make based on these raw materials which we have available to us. So just a few more seconds just to get some ideas on that, and you say you may well have written down, hopefully you've written down all the possible combinations of those. So all we're doing at the moment is just working out what the possible options are based on these raw materials we have available to build tables and chairs for our company called Swede Build. So you should have some combinations. There are really four main combinations you can build. So you could build 4 chairs, in which case you would then have 2 of the rectangular pieces left over. You could decide to build 1 table and 1 chair, in which case, again, you would have a rectangle left over. Alternatively, you could build 2 tables and 2 chairs, and you would have no pieces left over. Or the fourth option is to build 3 tables and no chairs, in which case you would then have 2 of the square ones, the red ones, left over. So what we've done so far is think about this company who want to build tables and chairs. They have these raw materials that could be used for tables or chairs. And what we want to do now is work out the options. We've done that. And I'm now going to give you a little bit more information on this. And I'm going to tell you that each of the square bricks costs £3, and a rectangular brick costs £5. So what I'd like you to do now is, for those 4 options which we've mentioned, work out what the cost is going to be to build those. At the moment, just work out the cost of the materials you've used. Don't worry about if you have any bricks left over. So remember, the 4 options are 4 chairs. The second option would be 1 table and 3 chairs. Third option would be 2 tables and 2 chairs. And the fourth option would be 3 tables and no chairs. So what I'd like you to do now for each of those options is to work out how much it's going to cost you to build the tables and chairs that you've got in each of your options. So again, just a couple more seconds for you to do that. and then I'm going to give you the final piece of information. So for each of those 4 options now, you should have been able to work out what the cost is to build each of those 4 options. So then just a reminder, first option is no tables and 4 chairs. Second option is 1 table and 3 chairs. The third option is 2 tables and 2 chairs. And the fourth option is 3 tables and no chairs. So now we've got the cost. We understand what the options are based on our raw materials, what we could do with those raw materials, how many tables, how many chairs we could build. I've then given you some more information, which is how much each of the raw materials cost, so how much each square brick costs, how much each rectangular brick costs. So you've now got an idea of the cost. So now the final bit of information in this particular exercise is to then work through how much we could actually sell them for. So each table sells for £32 and each chair sells for £21. So now what you can do is work out for each of those 4 options you've got how much you're going to sell them for. So for 4 chairs, working through that one, a chair sells for £21. So 4 chairs means that you will be able to sell those 4 chairs for a total of £84. Similarly, if I go to the fourth option of 3 tables and no chairs, then 3 tables will sell for 3 times 32, which is £96. So work through those. You've then got for each of those 4 options, you've then got how much each of the options cost. So remember I told you how much each of the bricks cost, so each of the raw materials cost. So for the 4 options, you work out the total cost. You've now for each of the 4 options worked out how much you're going to sell these tables and chairs for. So question number 4 is which combination of tables and chairs will give you the greatest profit? So a couple of minutes for that, and then I believe, Eve, that there is a poll on this as to which, so that people can guess which they think or work through the maths and work out which is the most profitable.
Yep, there is. So it'll cover up the slides. I'll give it a few more seconds and then I'll launch it.
The other thing I forgot to mention is if you do have any questions or comments, please put them in the chat window and we will answer those throughout the course of this. So a couple more seconds in terms of which do you think is going to give you the most profit on this, and say if you have any questions on this or any comments, please put them into the chat window and we will answer those for you.
So the question should now be on your screen. Let us know which combination you think is the best combination.
I think you must all be working through the maths still, are you?
I'll give you a couple more seconds. And then if you haven't answered, we'll assume that you've got the answer right, but you're too shy to tell us. Okay, I think we'll move on now. So do have a go at the polls throughout the session. Back to you, Matthew.
Okay, thank you. So you must have all been too shy to actually put the answers in there. But I can give you the answers, and all of the material, we should have said all of the material which we've been using is actually available. So if you wish to do this afterwards, do feel free to do this afterwards. So if we move on now, and Eve, I don't know if you can remove the poll. It's still on my screen. I'm assuming it's on everyone else's screen as well.
Oh, it should be closed now.
Okay. So I will give you the answers so that if you have done it but too shy to answer the poll, if you did 4 chairs, the profit you would make, bearing in mind the costs and how much you'd sell them for, the profit would be £40. If you made 1 table and 3 chairs, the profit would be £46. If you made 2 tables and 2 chairs, the profit would be £52. If you made 3 tables and no chairs, the profit would be £48. So the one that makes most profit is 2 tables and 2 chairs. Now you may say, well, that's all very well, but what about the materials we had left over? So if you did make 2 tables and 2 chairs, you would have no materials left over, so you'd have no Lego bricks left over. But all of the other options, you would have some of those bricks left over. So what we've done is basically said you could deduct how much those raw materials were, assuming that you were going to not use them for anything else. However, the result will still be the same, that 2 tables and 2 chairs is the most profitable. So this is all about Maths Week England. This is all about using maths. Whilst it would be nice to continue to build with Lego, what we want to consider is what is the real world application of this. So Swede Build as a company wants to make as much profit as possible. But the amount of resources they have available to them, obviously we're using Lego bricks in this case, but they could have wood, metal, all sorts of material. So the resources they have available limits the possibility. So that limits how much profit potentially they could make. So that is what is called a constraint. And constraints are very important because that then helps organizations understand what are their limits. But let's take this to Swede Build, IKEA in another example. What happens if there was 800 bricks or 6 million bricks? What happens if instead of having just 2 types of raw material, they had 25 different types of raw material or 250 types of raw materials? What we want to be able to do is build some form of mathematical model or some algebraic equations which help us understand and work out what may well be the optimal solution. So we're actually going to do this now for the Swede Build, so the Lego furniture factory. And what I want to do now is actually build that algebraic equation. So what I'm going to say now is I'm going to say let the letter T represent the number of tables produced and C be the number of chairs produced. So what I'm doing now is forming, so rather than working through each of those 4 options as we did, I'm now going to form a general equation to illustrate or to show me what those constraints are. So the letter T is the number of tables produced and the letter C is the number of chairs that are being produced. So let's think about that. If you want to do this, I will give you the answer in just a few seconds, but what I want to do is actually write down an inequality that links the number of tables and chairs to the number of rectangular bricks. So what do I mean by that? If you remember, for each table that we produce, we use 2 of the rectangular bricks. For each of the chairs that we produce, we use 1 rectangular brick. And we have 6 of those in total. So T is the number of tables, and for each table we produce, we use 2 bricks, and C is the number of chairs produced, and we use 1 for each chair we produce. What I'd like you to do is think about what is the inequality, in other words, what's the type of equation that would illustrate the constraint that we have. So we have 6 of these bricks in total. We could use these to produce tables or chairs, where T is the number of tables and C is the number of chairs. Similarly, for the square bricks, remember for a table, we use 2 of the rectangular bricks. For a chair, each chair we produce, we also use 2 bricks. And in total, we have 8 of the square bricks available. So again, think about an inequality, think about an equation which will help to express the constraint we have. So remember, the constraint is saying we have a limited number of materials which we could use to build either tables or chairs. And what we need to be thinking about is how can we express that constraint, in other words, total number of bricks available and the number of tables and number of chairs that we could build. So again, just a couple more seconds and then I'll give you the inequalities, and that will then take us on to how we can actually solve this problem. Much as it would be great to be building models all afternoon, we want a way to express this in algebra. So an algebraic equation which will help us understand these constraints we have. So I'm sure most of you will have reached this point by now. And so the inequalities are for the rectangular bricks, the number of tables. So remember, for each table, we use 2 of these bricks, and a chair, we use 1 of these. So 2 bricks times the number of tables plus 1 for each chair we use has got to be less than or equal to 6. So we have 6 bricks in total. The number of tables we produce and the number of chairs we produce, 2 times number of tables plus 1 times the number of chairs we produce has got to be less than 6. Similarly, for the square bricks, we have 8 of those. We use 2 for each table and 2 for each chair. So 2 times the number of tables we produce plus 2 times the number of chairs we produce has got to be less than or equal to 8. So if you think about this, if we to produce 2 tables, 2 chairs, we're going to use all of the bricks. And so we're going to have 2 times the number of tables plus C. So that's, remember, for each table we use 2 of these. So that's 2 for each table we produce, and then 1 for each chair that we produce. And that has got to be less than or equal to 6. So why have we put these together? Obviously, it helps us in terms of understanding the constraints we have. So how can we best use those resources? But obviously, the other thing we want to be able to do is work out a way that we can actually solve what is the best solution. So remember, at the end of the day, what we're trying to do was make most profit. So what we want to be able to do is, we've got these inequalities, how can we then maximize the profit we're going to make? So you may want to think, because we've got these 2 constraints here, let's actually think about how we could graph that, because we've got 2 constraints and we've got 2 raw materials. So think about how you might want to plot this. So for these rectangular bricks, if we said that 2 times the number of tables plus 1 times the number of chairs equals 6. What I'm trying to do is just sort out the extremes on the graph here. We can then say if the number of tables we produce is 0, what does that mean? C can equal, and then similarly, if we produce no chairs, what are the results there? So you can see on here that if we just produce chairs, so we produce no tables, then the answer is 6. So the second line there in purple. Similarly, if we just produce tables on here, we can produce 3. So 2 times 3 equals 6. So what I'm trying to do here is just how we can actually plot these inequalities we had on a graph. And we're obviously going to do the same for the square bricks, so the red bricks on here. And remember that what we said on here, that the 2 times the number of tables plus 2 times the number of chairs have got to be less than or equal to 8. So what we're doing is we're going to make it equal at the moment to work out what the extremes of these could be. So what we're doing is really starting to plot the coordinates on a graph. So you can see here in terms of the square bricks on here, then if we produce no tables, then we can produce 4 chairs. Similarly, if we produce no chairs, again, we can do 4 tables on that. So what we might want to now do is actually plot these on a graph. So the reason for doing those, what you might call the extremes there, of setting one of the values, so for example, in this case, the number of tables, second row on this, number of tables to be 0, how many chairs? Similarly, if we produce no chairs, how many tables can we produce? If we then plot those on a graph, and we probably haven't got time to do this now, but obviously feel free to do this afterwards. So what we can do here, if we look at the blue line on here, so let me just go quickly back to the blue. So this is the rectangular bricks, don't forget. So on here, we said if we produce no tables, we can do 6 chairs. If we produce no chairs, we can do 3 tables. So plotting that on the graph, you can see the x-axis here is the number of tables on here, and the y-axis is the number of chairs. So for the rectangular bricks, if we produce no tables, we can produce 6 chairs. If we produce no chairs, we can make 3 tables. So the blue line is going from 6 on the y-axis to 3 on the x-axis. So that is the line that we've drawn on there, where it crosses the y-axis at 6 and x equals 0. And similarly, when y equals 0, it crosses at 3. So the blue line there is all of the possible values there could be. And you note, if you remember, the constraint originally was 2 times the number of tables plus 1 times the number of chairs is less than or equal to 6. So it's anything below that blue line. We've obviously done the same for the square bricks. So this is if we produce no tables, how many chairs can we produce? And that's 4. So therefore we're crossing the graph at the value of x equals 0 and y equals 4. And if we produce no chairs, then in terms of the square bricks, we can produce 4 of those. So in this case, it is crossing at the value of x equals 0, y equals 4, and then also crossing the x-axis where x equals 4 and y equals 0. So again, because the constraint was 8 is the maximum number of square bricks we have, and 6 is the maximum number of rectangular bricks we have to be looking below those 2 lines. So what we've now got is 2 lines on the graph, and we know anything below those lines are what we call feasible solutions. So what we now have is anything below those lines would be the relevant area on there. So we've now got the graph, but if you notice on the graph, just in terms of plotting, although we've crossed, for example, the red line at x equals 0 and y equals 4, we've actually continued it slightly to the left. And similarly, for the red line, we've crossed it at y equals 0 and y equals -1. So we will try this. I think there's a quick poll here. Please do answer it. What we'd like to now say is, on the graph which I've just shown you, we actually had negative values. Do you think negative values could form part of the solution?
That poll is now live, so please do make your best guess if you're not 100% sure what the answer is.
We'll give this a few more seconds, but it looks as though we have 100% correct at the moment.
Yeah. If you're feeling brave and you think you know why, you know what the answer is, feel free to type it in the chat.
Okay, I think we've got 100% answers there, haven't we? 100% correct answers, should I say.
Yep. Fab.
So thank you for that. So yes, you're absolutely right. Because we are working with these actual raw materials here, in our case, we've got these bricks. Anything that's in the purple area are considered the feasible region. So remember, again, just to repeat, in terms of the y-axis, the red line crosses at 4 and x equals 0, and the blue crosses the x-axis at y equals 0, obviously, and x equals 3. So anything in purple is what's called the feasible region. So these are the feasible solutions. We haven't got negative raw materials. We actually have actual raw materials, so therefore we can't have negative answers. And so that's why all of the feasible options are in the purple region. And each of the diamonds which are on there are potentially showing solutions on there, so combinations that could be made. And you may well be thinking, well, how do we work out the optimal solution? And what you want to work out is where is the most extreme one. So remember, when we actually did this as a building exercise, we actually had 2 tables and 2 chairs as the optimal solution. And so you can see this on the graph. So what we've done is taken an actual model building in terms of deciding or working out by building and trying what the possible combinations were. We then converted that into some algebraic formulae, which are called constraints. And then we've used those constraints and graphed those to be able to put those and work out what is the optimal solution using algebra. Some would say not quite as much fun as actually building, but if you think about this was 2 raw materials and a limited number of combinations. Imagine, as I said before, if you had 250 or 2,500 different types of raw materials, and you had, let's say, 20 different pieces of furniture you could make, then it becomes a lot more difficult to do that by modeling. And that's when algebra comes into play. Great. So what does this all mean? Why have we done all of this? This is a type of maths which is called linear programming. And what we're doing with linear programming is finding the best solution from a set of constraints. So what we've done so far is we've actually built a series of constraints. And then what we were interested in was finding what the most profit was. So in that respect, the best solution for us was what is the maximum profit we can make. But we had a series of constraints. We were constrained by the amount of raw materials we had. So we built a couple of constraints, and then we understood what was going to be the most profitable solution. So how is this worked out, and how is this used? If you think about a lot of situations, you may be wanting to say, well, how can we help provide low-cost, healthy food packages to people in need? So I'm not going to go through in terms of exactly what the answer might be, but just think about, in this case, what the constraints might be. So thinking, you might say, well, low cost is important, but it also has to be healthy. So how can you work out what some of the constraints might be on there? So would it be cheaper, for example, to buy some certain foods in bulk? Does that reduce your costs? But if you don't distribute that, does the food go off? So what you need to be thinking about whenever you're considering something like a linear program is working out what the constraints may well be. So as Eve said at the start of this session, this is all around operational research. So I don't know if we've got a poll for this. If not, perhaps put it in the chat as to how many of you have actually heard of operational research.
We do have a poll for this, so that should be appearing on screens now.
Not quite sure whether people have heard of it or not. Okay, we'll make the assumption that people don't want to feel that they don't know what operational research is.
Yeah, I'll end that poll now.
So what is operational research? Operational research is using maths and mathematical methods, of which linear programming is one, to help improve decision making. Another way of expressing that is the science of decision making. Think about the current pandemic we're in. How do people make decisions? Are they using mathematical techniques to help them understand the situation and help them to make decisions? So operational research, and I say linear programming is one of the techniques that we use within operational research to help people make better decisions. So better decisions, more optimal decisions, decisions which are more applicable, more appropriate, and they're using data and problem solving techniques to help them improve that. So a couple of examples here. Supermarkets. We're all going to supermarkets still, but supermarkets use operational research a lot. So they may be looking at things like what products people are buying. What products do people buy together? You may have heard of a term called basket analysis. And this is understanding what products people buy together. Now, why is that important to a supermarket? That's important to a supermarket because if they know that people quite often buy red Lego bricks every time they buy blue Lego bricks, they should put those products together in the supermarket. And that might mean that they can then increase the sales of both of those products by having them together. So this is understanding what products people buy. Similarly, they may want to do things like special promotions. So if you buy a red Lego brick, we'll give you 50% off a blue Lego brick because they know that people buy those products together. Other examples of where operational research might be used within a supermarket could be, for example, how many checkout staff are needed or how many staff are needed generally. So they obviously know that things like Friday evenings are particularly busy, the weekends are busy, so therefore they need more staff and they need more checkouts. But if they're trying to keep their costs down, they don't want to have more checkout people working if there's nobody going to the checkouts. So what I mean by that is they don't want to have all of their checkouts fully manned with people if the store is going to be very, very quiet. So they're looking at data, they're trying to understand what times people are buying. Another example would be how many products should they order? So the example I always think about on this is in June, how many lettuces should a supermarket buy? So think about that in terms of what are the constraints? The constraints might be the number of lettuces that are available. It's not just an infinite supply of lettuces, so how many lettuces are available, but they might also look at things like the constraints. So what is the weather going to be? Is it going to be sunny at the weekend and people are going to want to have salads? But they also need to think about delivery times. How many delivery trucks do they have? Where are those delivery trucks? How do they get those products from the people growing the lettuces to the supermarkets so that people can buy them? Things like lettuces go off within a couple of days. If you think about tins of beans last for a long time. Lettuces don't. So therefore, they have to be as accurate as they can be in terms of how many of those products they want to buy. Another example could be airlines, where people want to go and when. Hopefully, we'll all be going somewhere fairly soon on an airline, but airlines are interested in where people want to go and when they want to go. Airlines do a lot of work in terms of ticket prices. How expensive or how cheap should they sell their tickets? Now, you could say, well, that's just a simple supply and demand. The more people that want to go somewhere, the higher they put the tickets. But they may be flexible, so they might think that they're going to have a certain number of people going to Paris on a Monday, and they find on the Friday that not as many people want to go to Paris. So therefore, they might think about reducing the prices. So they are looking at this in terms of how many people want to go, what ticket price should they sell, and bearing in mind that ticket price could change over time. Similarly, they want to understand the best way to board a plane. So this is called simulation, and what they do here is understand how people flow. So if you're in a terminal and you go to the gate when your flight is announced, what's the best way to board people onto that plane so that they can actually board as quickly as possible, as safely as possible? And this is what's used called simulation. And simulation is where you actually build a model. A lot of operational research is geared around models and building of those models, and you actually look at the flow of people. Healthcare is another example of where operational research is used. Similar examples, you may want to think about how do we reduce waiting lists? How do we use hospital resources? So resources could be in terms of number of operating theatres, but also the number of staff and the skills that those staff have. Particularly relevant at the moment, obviously, in terms of have we got enough staff with the right skills to be able to treat the types of patients that we have coming in to the hospital. So a lot of work is done in healthcare. So this is all operational research. It's all around when a decision is particularly complex or it's actually unclear what the main problem is. And when you don't know how well things are going, or you think they could be done better. So you think about the current situation we're in. How do people change what they're doing? How do organizations change what they're doing? They may want to say, well, we need to slow down production, but if they slow down production, do they need as many staff in place? Do they need to do additional training? Do they need to change what people are doing? So operational research is used when a decision is particularly complex and you need to understand. So if you think about this, you need very frequently, if not every time, you need some data. You need to understand the situation. You need to understand what the problem is. What is the problem you're actually trying to address? And then you can apply some mathematical techniques. Linear programming is the one we've done today to help us understand what is the best solution coming out of this. So I've mentioned simulation already. What if? So if you think about the checkout example in the supermarket, you might say, what if we reduce the number of checkout staff by 10 on a Friday evening between 6 and 7 o'clock? We know approximately how many people come into the store at that time. Can we actually model what that will mean in terms of the length of queues at the checkouts? Optimization is where you're looking for the best solution. So yes, we may want to simulate or model how many checkout staff we need to understand the different scenarios. What if we increased it by 10 or reduced it? Optimization helps you understand what the best outcome might be. So here's some examples. It's not every single company. There's an awful lot of companies that use operational research. We do have to point out these are not necessarily organizations endorsed by the OR Society, but just to give you an idea of the types of careers that you can have with operational research. So you can see a lot of very large organizations, a lot of varieties of organizations where operational research is used. So I just thought I'd tell you a little bit about myself just to finish off this session. So I started many years ago at a company called British Steel, which no longer exists and was then renamed and taken over by a company called Chorus, which was then in turn taken over by a company called Tata Steel. And we were doing projects there, which was things like if you are cutting a certain length of iron girder, in simple terms, how could you then cut that up? And what I mean by that is, supposing the length of iron girder that was manufactured was 100 meters, and you had an order for 20 bars at 4 meters and 1 bar at 30 meters. What's the best way to cut up the 100-meter bars to satisfy those orders? So again, an example of linear programming. What's the constraints? What's the optimal solution on that? I then went to work for a water company, and an example of a project we did there was the reservoirs we had. How could we work out the best way to move water potentially between reservoirs to satisfy the demand there was? I also did a project which is around waste management. What's the best route for trucks picking up waste management to be able to pick up all of the waste that need to be picked up in the shortest distance? Then went to work for a couple of consultancies, but also a bank on there. So you see NatWest on there. And this was looking at things like branches. Where should we have the branches? Which is the most profitable branches we have? Then worked for a travel company, and this is where some of the examples I talked about before. So things like ticket pricing came about. What's the optimal way to price tickets on that? And then I did a short piece of work with a waste management company, and then I've come to finish working for IBM. So I was part of a company which was taken over by IBM. So what's the type of work I do? These are some of the examples of companies I've worked with over many years, not all within IBM, but certainly within the organizations I talked about. So again, you can see a wide variety of companies there. And to give you just some idea of some of the current projects that I'm working on at the moment, I'm working with a brewer at the moment. I'm not allowed to tell you details of exactly what the projects are, but just to give you some examples of where a brewer might use some of the operational research techniques. This could be things like how many pints of different types of beer should we be brewing? What's the best route for our delivery trucks to take to drop the beer off at the right pubs when they're open? I might want to be considering, should we be looking at other markets? Should we have some new pubs somewhere? An aircraft manufacturer, types of projects we're doing there will be things like, is there a faster way to build an aircraft? So obviously very complex pieces of machinery to build, very complex in terms of the number of tasks and number of how do you get all the raw materials in the right place at the right time? Could we be manufacturing those more cheaply? An infrastructure organization in the transport area. And again, this could be things like timetabling. When should we have the trains, buses, etc. running? Do we know how many we need? When should we do repairs? When's the best time to do those repairs? And a utility. These are just some examples of organizations I'm working with at the moment. So again, you can see a wide variety, but all of which have that common situation of there is a problem to be solved. We want some data, we have some data. How can we use that data and some mathematical techniques to help us solve some of those problems and make better decisions? So that could be in terms of more profit, or it could be in terms of reducing costs, or it could be, for example, in terms of the utility, how do we increase our customers? How do we attract customers to us as an organization while still making money on that? So just to finish off, how do you get into operational research? What are some of the elements to consider? It is fair to say operational research does have its basis in maths and statistics. So obviously maths GCSE A levels are always a very, very good start to operational research. But also remember, I said before that operational research is also around understanding what the problem is. So in terms of when we built the graph for our Swede build company, you could have obviously plotted that on a piece of graph paper because we only had 2 dimensions, which was tables and chairs. When you've got 200 dimensions and 20,000 different raw materials, there are obviously computer programs that do that, but you need to have that mathematical, logical type brain to understand what the problem is, and then you can use computer programs to do a lot of the number crunching, as it were. So once you've thought about that, obviously a good classification in a STEM type degree is always beneficial. Master's degree, there are a lot of master's degrees in operational research, or occasionally called things like analytics, business analytics. Whilst that is desirable, not necessarily essential. It's more about the aptitude that you have for problem solving. So again, just thinking back to some of the examples I've taught through, a lot of work around operational research is what are the constraints? What is the problem you're actually trying to address? So just before I hand back to Eve, just to finish off with some of the resources which may be available to you, I'd just like to say thank you very much for your time today and your attention. Hope you enjoyed doing Swede Build, Lego Furniture Factory. And I'll now hand back to Eve in terms of if there's any questions which come through on the chat, but also she will give you where you'll be able to get additional resources and additional assistance. So thank you very much.
Thank you very much, Matthew. That was a really interesting workshop, and hearing about your career at the end was really cool as well. So if anyone does have any questions, feel free to pop them in the chat and we can answer them now. And if you would like to learn a bit more about operational research or the resources that we've got available, the best place to go is the link on the screen at the moment, theorsociety.com. On our website, you'll find information about all of our resources, so you can download everything you need to run this workshop, or we've got other workshops you can use. We've also got videos. We've got videos on YouTube and on our website that talk a bit about different examples of OR, different case studies, careers talks. So yeah, it's really worth having a look at all of that. And while we're waiting for you guys to ask your questions, I guess I'd be interested to know what project you've worked on, Matthew, that was your favourite or you thought was the most interesting.
Oh, there's an interesting question. I actually did a project for a manufacturing, construction, should I say, construction company, which was interesting, but that was primarily because it was actually abroad and the way they worked was slightly different. But I think probably the most unusual one was for a chicken farm. And you may say, well, what's so special about a chicken farm? This was a company that reared chickens, which then went into things like ready meals. Now, the problem with chickens is from an egg being hatched to a chicken being fully grown takes about 6 weeks. So they were having to predict 6 weeks in advance how many chickens they thought people like Sainsbury's, Tesco's, Waitrose, all of the supermarkets were going to need. Now, obviously, they worked with those supermarkets, but going back to the example I mentioned about supermarkets, if it's the middle of summer and all of a sudden we have a heat wave, then more people are going to want to do things like barbecues. So therefore, the demand for chicken legs is going to increase because people want to barbecue them. So we worked with them to help them try and understand what were some of the factors that would influence the number of chickens they needed to rear to sell in 6 weeks' time. So obviously there's a longer term planning as well, and they had some ideas of what was going to happen. But then they may also have the situation that a supermarket comes to them and say, we're going to do a special promotion on our ready meals in 2 weeks' time, and therefore we're going to need extra chickens. So how do they cope in that situation, and what do they do? So a lot of that was understanding things like how many chickens they could. They still called it manufacture, although it was actually rearing chicken. They called it manufacturing chickens. How could they understand what the demand would be, and bring in other factors like the weather and weather forecasts in to help them have a better understanding of how many chickens might be required in 6 weeks' time. So that was probably one of the most interesting ones. There's a lot more to rearing chickens to go in ready meals than perhaps you think there might be.
That sounds like a really interesting, complicated problem to tackle with all the different factors that you had to think about.
There's a lot of different elements to it, and it was almost easy to think, well, surely you just need to rear so many chickens, but it was fluctuating, and the demand would increase and decrease based on a number of factors, some of which I've mentioned. So it's how do you incorporate all of those factors into that?
Well, we don't have any questions in the chat, so I can only assume you've done an excellent job and nobody wants to ask anything because they've had all the questions answered already. I think the one last thing that I should mention is that if you would like to learn a bit more or you've got any questions afterwards, you can contact me by emailing education@theorsociety.com. And I think we can wrap it up there and let you go back to enjoying the rest of your day and the rest of Maths Week England. So once again, thank you very, very much, Matthew, for giving this presentation. And thank you, everybody, for coming along and listening. I hope you've enjoyed it.